Hello there, how's it going? Welcome to the lecture on basic analog sound, the fundamentals, if you will, of the substance which we work with in the studio in the sound recording and production realm, audio, if you will. Fundamentally, sound is an analog thing, okay? So we have to sort of get used to that reality. It happens in the air. And so let's start off with the very most essential elements of audio, and that is the simple fact that sound, as we know it, the sound of my voice that you are hearing, any sound that you are hearing, is the result of compressions and rarefactions of air molecules. So air molecules, as it turns out, are rather springy things. So if you can imagine, this room is filled full of balloons, and the sound basically is those balloons getting smushed together and then opening up. So this compression and rarefaction of air molecules, that is essentially what sound is, and that happens if you have a source that is creating a sound. For instance, when I clap my hands, boom, then air molecules are being affected from that point spherically from that source. So they emanate spherically from the source when I clap my hands. It's not like there's this wave that looks like this. It goes like this, and it happens spherically in that realm. So it's like 3D ripples in a pond. That's the best way to sort of explain what a sound really is. So and these compressions and rarefactions form a waveform. And that waveform can manifest itself as repetitive, which would sound like a tone, or a non-repetitive waveform, which would sound like a noise. And there's all kinds of variations in between the two, obviously. The more squished together those air molecules get, for instance, if I really smack my hands together, those waves emanating from my source are going to really squish together the compressions and then have more serious rarefactions. And that's going to create a waveform that's going to have a larger amplitude, which means louder. Amplitude and loudness is directly correlated to the amount and tightness of the air molecules as they do this compression and rarefaction action moving in the spherical realm. This amplitude of the sound wave, we measured this as a pressure, and it's measured in the Pascal units. And pressure also correlates to voltage. One of the magical things about sound in the air is that it can be reproduced electronically with alternating current. Of course, this is what makes recorded audio even possible. The simple fact that the sound in the air can be recreated as voltages in alternating current. Without that, we have no recording. Can't even consider the possibility of it. So, fortunately, that works that way, and we're very happy about that. The thing you got to understand, though, about these waves that we're talking about that emanate from the source, when we sort of have to sort of express these in some sort of a physical manifestation, in a drawing, if you will, we sort of tend to make these what we would call a transverse wave, which would be kind of like taking a string and moving it like this. The idea that the wave sort of moves down the string like this. And that's not really how these waves actually work. They're actually longitudinal waves, and they move back and forth. So you have to imagine more like these waves are coming out from the source going like that rather than like that. Now it's kind of crazy to try to explain it that way. The idea of the spring, that's the way that works with the compressions and rarefactions of molecules more than the idea of the string. Spring, not string. So longitudinal waves. But still, it's really hard to draw a longitudinal wave in a way that makes any sense. So we tend to use the transverse wave to describe a longitudinal wave when we're talking about audio. When you see these transverse wave drawings, imagine a longitudinal, and that'll make it a lot easier to deal with. As a result of all this, we end up with waveforms. These waveforms can, as I mentioned earlier, be repetitive, or they can be non-repetitive, and combinations of the two. That's the difference between a tone, something that sort of manifests itself as a pitch or a tone even, or just a straight up noise. So let's talk about what happens if we have a repetitive waveform. We hear a lot of repetitive waveforms in nature and in the world, and so let's sort of address those first. So the rate that a source oscillates, we would call that the frequency of a sound wave, and we measure that in hertz, or cycles per second. And that corresponds to the length of the cycle. It corresponds to the length of the period of the wave. The shorter the period, the higher the frequency, and the longer the period, the lower the frequency. The distance between the peaks of the compressions and the rarefactions, we would refer to that as being the wavelength of the sound wave, and we would measure that in feet or in meters. Another descriptive term for the sound would be the time that it takes to complete one single cycle, and that would be the time between peaks, and we call that the cycle, and that's measured in seconds per cycle. We have these different ways of measuring our sound waves. These pretty much cover the pitch or the frequency, the wavelength, the actual physical wavelength of our waveform. And we also are dealing with the amplitude. Frequency and cycle have an inverse relationship. 1 over the cycle equals the frequency, and 1 over the frequency equals the cycle. And then if we want to find out our wavelength, then we have to look at what the speed of the sound in air is. And as it turns out, speed of sound in air is about 340 meters per second, or about 1,130 feet per second. So these are two numbers that you want to kind of commit to memory when you're dealing with audio, because we're always going to be using these when we're doing any kind of computation of wavelengths. At freezing, 330 meters per second. Yes, there's a temperature relationship here, but we generally deal with 340 meters per second. The way we figure out the wavelength is we take the speed of sound, in this case, again, 340 meters per second or 1130 feet per second, and we divide that by the frequency. So that then we can also work that the other way around. We can figure out the frequency of a sound by taking the speed of sound and divide it by the wavelength. So these are ways that we can sort of move back and forth to figure out different properties of our sound. And just to give you some idea of what we're talking about with wavelengths here, a kick drum gives about a 60 hertz tone, maybe perhaps. That would be a 19-foot wavelength. So it takes 19 feet for that wave to complete a full cycle. A tuning note like A440, that's going to take, that wavelength of that cycle is about 2.6 feet. The sibilance of your voice, like that around 5K, 2.7 inches. That's how big that wavelength is. That talks a little bit about frequency, about wavelength, a little bit about cycle, about period. Let's talk about harmonics, because a lot of sounds aren't just sine waves in nature. They don't just sort of sit out there and go little toodly-too. Although all sounds can be broken down into component sine waves. Most sounds that we are hearing in nature have other harmonics or overtones or partials. A lot of our sounds are made up of multiple sine waves of multiple frequencies. And a lot of times these frequencies are related. In fact, when we're talking about harmonics, we are talking about our fundamental pitch of our waveform times 2 for the second harmonic, times 3 for the third harmonic. These are all integer related. A lot of our harmonic series, that's how it's derived, basically by just simply taking our fundamental tone and multiplying it by integers. The 7th harmonic of a sound will be that frequency times 7. The 14th harmonic of a sound will be that fundamental times 14. Again, these apply to repetitive waveforms. Harmonics are integer related. If we're talking about the difference between harmonics and overtones, it's important to make sure that there's a distinction there. The second harmonic is the first overtone. We don't count the fundamental in that when we're talking about overtones. So second harmonic of a pitch, if I give you a pitch, then the second harmonic of that is going to be the first overtone. So if we're talking about overtones instead of harmonics, it's just going to be harmonic minus 1. There's also other possible tones that we can have over our fundamental, obviously, and like we would call those partials, and those are not integer related, and we would call those inharmonic. A good example of that would be the peal of a bell, for instance. If you hear a bell pealing, a lot of times that extra tone on top of the bell is not integer related. It's usually a little bit different than that. So that would be a partial. If we're talking about non-repetitive sounds, we're talking about noises. For most of the times, we're talking about two kinds of noise: white noise and pink noise. Now, there's all kinds of different colored noises in different programs. You may come across in your DAW some things like blue noise and gray noise and the dreaded brown noise. Avoid the brown noise. We deal with white noise and pink noise. And the difference between those two, in case you're wondering, is that white noise has equal energy per bandwidth. That means from 0 to 1K, 1K to 2K, 2K to 3K, 3K to 4K, 4K to 5K, all of those have the same amount of energy. Pink noise is equal energy per octave. And what that means is that from 0 to 1K, energy, from 1 to 2K, same energy, but then not from 2 to 3K, same energy, but it's 2 to 4K, because then we start doubling it for octaves. So 2 to 4K, same energy, 4 to 8K same energy. So you can see right off the bat, as we're going into upper frequencies, we're losing relative energy to the white noise. White noise is the same energy every bandwidth. As a result, pink noise has less upper frequency material and sounds bassier as a result. The sine wave is our fundamental sound. It's just like one frequency. It's the sound of, if you've ever heard a sine wave, it's a pretty pure tone. It's kind of piercing. A flute probably or a piccolo gets you the closest to that. It has just a fundamental, and it has no overtones, no partials, no nothing. It's just basic. Can they be useful? Yeah, I like those for really low bass, and I like them sometimes for solos. They'll cut through anything. But then we start adding some overtones and some of our harmonics to it. And if we just add odd harmonics and we do it just a little bit of those, we end up with a triangle waveform. It sounds very much like a sine wave, but it gives us a little more stuff on top of that, and we can actually filter that, use a filter on that if we want to. If we go another level and we have a whole bunch more of our odd harmonics, the third, fifth, seventh, the third harmonic is 1/3 of the amplitude of the fundamental. The fifth harmonic is 1/5 the amplitude of the fundamental. Then we'll end up with a square wave. And square waves definitely have a lot we can filter from. If we then add in odd and even harmonics, then we can end up with the great sawtooth wave. And that's the more frequency-rich wave. So those of you who have synthesizer are probably familiar with these terms. These are basic synthesizer waveforms that are easily created in the synthesizer realm, pretty much, again, by taking sine waves and adding them together. So let's talk a little bit more about this repetitive waveform, because keep in mind this waveform goes into positive and to negative territory. It goes on both sides of zero. When we're describing a cycle of a waveform, we'll describe that in terms of either pi radians, or we'll describe that in terms of degrees. Once we've completed the cycle, that's, for instance, 360 degrees. If we get, after the first half of the cycle, that goes up and then comes down and hits zero, at that 0 point, we call that the 180 degree point. The very top, we call that the 90 degree, and the very bottom, we call that the 270 degree point. And this is just a way, again, that we are trying to describe something that actually exists in a different format than we're describing. We're trying to sort of two-dimension what is really essentially a three-dimension activity, but this is the best we can do. So we call this phase. In other words, what part of the waveform that we are actually currently in that moment of time is what part of the phase. For instance, if we have the same sound coming from two different sources, then our ear is going to hear the same waveform that's coming from those two different sources at two different points of phase. Might hit the first time, might hit a little bit further up on the waveform when it hits the ear. It may be at the 270 when it hits the ear from the second one. Those would be summed up in the ear, and the result would be what you would hear. It would either be in phase, where it would be coherent, or they could even be out of phase. And what do I mean by out of phase? We have two signals that are in phase. In other words, they are coming from you from the same source at the same time, and they're hitting your ear at the exact same time, at the same point in the waveform, this part of the waveform. If they hit you at the same time, then what's going to happen? It's going to double in amplitude. It'll sound twice as loud. If it's somewhere in between that and 180 degrees, they will sum, and they'll create a slightly different frequency as a result, because they would be not summing at the exact same point in their phase, as you can see in this graph on the slide. And you can even get it to the point where if both of those sources hit the ear and there's just enough of a distance so that those frequencies are 180 degrees out of phase with each other, then they will cancel out. That's when we talk about something being out of phase, is when something is 180 degrees out of phase with itself and therefore canceling itself out. And we can use that. That's a great little trick. We can actually use that trick to when we record in the studio, for instance, if we want to use a microphone in the studio and we don't want the stuff coming from the speakers, we don't want to use the headphones, we don't want stuff coming from the speakers to get into the microphone, we might take one of those speakers out of phase with itself, put the mix into mono, and then when it hits the microphone, although the person in the room will hear those speakers, the microphone will capture those, and those speakers will cancel each other out. It's a cool trick. That's how we would use out of phase as a beneficial thing. But for the most part, phase is not our friend when we're dealing with out of phaseness. We want phase to be coherent. We want phase to work together and to make things better and not make things worse. If we're dealing with like a time shift between two different sources that are giving us the same information, like two speakers in a PA system, if those two speakers are at a different distance from you, not exactly the same distance to your ears, it's slightly different distance from you, then there's going to be some phase cancellation. And we can actually figure this out by using the phase angle formula, which is basically 360 degrees times the frequency that we're looking at times the amount of delay that's happening between those two speakers, the time delay in time. And we can also figure that out for the distance between those two speakers. We can figure the time delay by going time delay equals the distance divided by the speed of sound. So again, we have some formulas here that we can use the same sound coming from two sources coming at us from different distances. We can figure out how far apart they are. We can figure out what frequencies are going to be a problem. We can address these issues. These are important for live sound applications, but it's also pretty important for our applications in recording as well. Although I don't think you'll have to do a whole lot of phase calculation, but you may find yourself doing a little bit now and then, and we'll see in later lectures why you may need to do that. A good rule of thumb when you're in the studio, for instance, is to think that sound travels about 30 centimeters or 1 foot per millisecond. I'm talking really roughly here. About a foot per millisecond, 30 centimeters. So keep in mind, if a second source is just 1 meter further away from the first source, it's going to be delayed by 3 milliseconds. So you can sort of use that as a loose sort of mathematical when you're trying to figure out some delay in the studio. If you have some microphones that are a certain distance apart, just what's going to happen with the frequencies. Can give you some idea of what's going to happen when you bring those microphones up and sum them together. So it's good to know about phase. It's good to understand how distances and how sound travels. 1 foot per millisecond. Pretty good way to think about it. For instance, you are in a room at your apartment, your dormitory, wherever you are. If you are recording somewhere, you are dealing with the limitations of your space. Your space has resonant frequencies that you will have to address at some point, because all spaces have resonant frequencies and they basically correlate to the dimensions of the room. And if you have a room and it has width, breadth, and height, you're going to have certain standing waves that will correspond to each one of those dimensions of your room that will end up speaking up. We can actually very, very easily compute those in general if you're so inclined to do that. And usually when I'm in a space that I know I'm going to be recording in, I'll do the measurements myself and sort of at least gives me some idea of what I need to be watching out for. Because we don't always get to record in a really great studio environment. A lot of times we deal with the limitations of our space and try to still get the best results we can get. How can we figure out the axial modes of our rooms? It's real simple. First off, what you want to do is get your measurements of your room, draw it out, and at least figure out the height, the width, and the length of your room. And the way we would compute this now would be, we would take half the speed of sound times the room node, which would be, let's say if it's the first room node that we wanted to do, and then we divide that by the dimension that we're talking about. So if it's 12 feet, so it would be 565 feet, which is half of 1130 feet. Remember, 1130 feet per second is speed of sound, times 1 for our first mode, divided by 12 feet. Whatever that is, that frequency, I'll then put that on my chart and sort of just draw a line there. Do that for the length, do that for the height, and then I would do that for the second mode and the third mode, maybe even the fourth mode. And I would just put those all on my graph. And then what you do is you look at your graph and you go, okay, anywhere that there are two of these lines within 5 hertz of each other, in fact, if I've got one mode that's at 90 and one mode that's at 92 or 93, that's going to be a problem area in my room, because if I get 2 of them adding up, they're going to boost. If they're dispersed, if I have all of these really well dispersed across, I'm perfect. But if I've got a couple of these nodes lining up real close to each other, those are the problem spots in my room, and those are the areas that I'll probably, when I'm mixing in my room, I find myself turning down a lot of that frequencies because I'm hearing a lot of it in the room off my speakers. I might have to go, oh, that's right, that's one of my modes. I better compensate for that. All good studios, although they don't have parallel walls, they still do have these modes, but they're dispersed out more. There aren't very many that are clustered. That's where the design of a console mixing room is really important, to really sort of disperse those nodes out, because they're going to be there. You can't get rid of them. They just can't be collected. So, anyways, hopefully that gives you some good information about standing waves. All right, so I want to talk a little bit about our waveform and about amplitude, because amplitude is definitely related to how loud things are, and how loud things are is rather important to what we're doing here. How do we measure loudness? One way to measure it is rather quite simple. What are the peaks? How big are the peaks of the waveforms? And we'll just sort of figure, okay, the biggest peaks, that's just how loud it is. I mean, whatever hits for the peaks, that's going to be it. But that's not a very accurate way to sort of describe a sound, because all kinds of sounds have lots of peaks, but they don't, like for instance, drums or anything with lots of transients, there's lots of peaks, but there's not a lot of stuff going on between the peaks. So it won't sound that loud, although it will register with a lot of volume. So that doesn't necessarily describe very well volume, just looking at the peaks, just seeing if it hits the red, for instance. So we could also average those peaks. We could also just take the sound that we're dealing with, our waveform, and look at it at periodic points, at regular periodic points, take those readings, and then average those out, and then say, okay, that's our volume. And that would pretty much give us a pretty good idea of what the volume is. As it turns out, the way that we perceive loudness is called RMS, or root mean squared. Again, we take these readings of levels at regular intervals of our sound, and instead of averaging them, we square them, we add them, we then divide that by the amount of samples that we took. And when we take these regular interval looks, we're also, a lot of times we're getting negative readings again, because remember, our waveform is going up and down, above and below zero. So sometimes some of those are negative reads. When we square those numbers, all of a sudden those numbers become positive numbers. And that helps us get a bit more accurate understanding of what the actual volume is, especially the way that we perceive it, because we perceive volume more root mean squared than we do peak or average. And view meters from analog machines were designed to read RMS and give you an RMS reading, again, because that's more of an accurate reading of what the actual volume is. So, but the ratio between the RMS that we figure out and the actual peaks, that's what we call the crest factor. And that sort of correlates to the headroom that we have in our system, and something that we want to keep our eye on and maintain good crest factor. And how much we compress something will reduce that crest factor. The beautiful thing of how this works is the compressions and rarefactions in air, we have figured out we can capture those with a microphone. We can take a diaphragm and stick it up there, and as those compression and rarefactions strike that diaphragm, the diaphragm goes along with it, and we've figured out how to turn that action of the diaphragm into electrical signals that we then express in alternating current. And this allows us, again, to have whatever we record out here possible on tape or on CD or whatever we're trying to record to. Makes it stick to something. This is good stuff. So we're trying to make sure we always have a great signal now. Now we understand how sound happens. We get it into the microphone, and now we're trying to figure out what to do with it. How to get a good signal. And what is a good signal? It's well captured, doesn't have distortion, it's honest, it's what's going in is what's coming out. It's expressed in a continuous voltage, and it reflects exactly what went into that microphone. How do we get this signal where we need it to be? Well, there's amplification, first of all, because a lot of times, if I'm talking really quiet here, we need to turn it up so we can actually get a good signal, and so that we can turn it down in the mix. So yes, we had to amplify. And originally we used valve tubes. The first ones were valve tubes, and we then later moved to solid state amplification. We got the level up. Then we created equalization. And originally equalization was created to make up for loss of frequency in a system. With the telephone lines, for instance, when we sent a message down the telephone line, once we got it to the other end, it didn't sound quite the way it did when it got in the first side. And so the idea was, well, let's put more high frequency on the front end so when it gets to the other end, it has enough. And this idea of equalizing the sound of the front end so it sounds like it's supposed to on the back end. Of course, we've changed that whole concept. But we also had to use this equalization just to get stuff onto a stereo disc, for instance. When we were cutting records, and we were cutting stereo records even before then, we had this thing called the RIAA curve. And just in a nutshell, when we try to put 22 minutes of music onto a vinyl disc, low frequencies really move those grooves, and that means we can't have as many grooves, and it makes it harder to record that. So we have to take off the low end and add high end to record it onto the disc, and then when it's played back on the needle, it adds back that low end and takes off the high end. And that's called the RIAA curve, and that was necessary to make it so that we can manufacture these discs and hear things off of the discs. Equalization made that possible. And then analog tape, here's another thing that we had to do to make the most of signals. As it turns out, we couldn't just put our signal straight on to analog tape. It didn't work very well.